We're back. Let's keep going. All right, now I broke this topic of torque up after the first two problems. The reason I did that because problems 3, 4, 5, and 6 actually deal with what's called torque equilibrium. Torque equilibrium. Now, torque is something that can cause rotation, but if you're in equilibrium, then you're not going to rotate. Well, that doesn't make any sense. You just said you're going to cause something when a torque causes it to rotate, and then if you have equilibrium, it's not rotating. Okay, let me give you an example. Okay. If I push here, that'll rotate it. Now let's say that you, out in the studio audience land, say, oh, I don't want you to do that. Stop that. Don't do that. I'm going to push down, and what are you going to do? You have a couple of choices. You can stop the rotation by either pushing up. Now, if I push here, and you decide to push here, you're going to have to put more force because your distance isn't as far from the pivot point. Or if I push here, you could put a force over here and therefore generate a torque. And that torque can balance out my torque. We're both applying torques. We're both applying a push, all right, that can cause this to rotate. But if we do that so they're equal and opposite each other, we can get equilibrium and we can get balance between those two torques. So you can get a torque equilibrium. And this number problem, we'll take a look at problem number 3. This problem number 3 is a torque equilibrium problem. Good problem. You will see these people. I'm telling you, okay? Okay, this is the last topic before the next academic adventure. You will see these. Yes, you will. Okay? Wink, wink. I was winky the other day. I'm winky today. You're going to see them. You're going to have to know how to do them. So let's do them. Get them right. Now, here we go. A 50 kilogram child sits on the left side of a 2-meter long seesaw. Now, back in my day, you can call it a seesaw, or you can call it a teeter-totter. Teeter-totter, seesaw. Same thing, whatever you call it. Potato, potato, tomato, tomato. Doesn't matter. So this is 2 meters long. Okay. So we got the kid sitting there. And the little kid. Now, okay, what else we got? 50 kilograms, 2 meters, 50 kilograms. So now 50 kilograms. That person is going to, I'll put an arrow representing their mass and therefore their weight. So they have a weight going down like this, and that's 50 kilograms. If you multiply 50 times 9.8, you'll get 490 newtons of force. Okay, that's their gravitational pull to the earth, their weight. And that weight is a force. Okay, that little kid's weight is a force, and that force is perpendicular to the surface of a seesaw. Therefore, it is a torque. So this person's weight is the force that causes the torque on the seesaw. Now we're assuming the seesaw's pivot point, the fulcrum, is right smack dab in the middle. All right, so what else we got here? What's the question, for crying out loud? We're just setting it up. Okay, if the pivot point we're set in the middle, okay, we got our fulcrum in the middle, then a 120 kilogram adult is going to sit on the other side. Okay, now you know that this is not going to be even, right? 50 and 120, you know, you've been on the seesaw before. If you're a little kid and you're sitting on one side and some big kid or an adult comes and sits on the other side, if they sit on the opposite side, on the far away as possible like you are, what's going to happen? You know. And maybe the kid will go flying. It's all fun and games until somebody goes flying. Okay. So what's going to happen? This adult is going to have to, you know this, they can't sit here. They're going to have to sit somewhere in here. I don't know where. So somewhere in here, they're going to have to sit in order to cause balance. So we want to balance the seesaw. If I put the adult here, not balanced, boom. If I put the adult here at the pivot, not balanced either, boom. But the person is going to have to be out in here somewhere to balance this off. And that's what we're trying to figure out. All right, how do you do a problem like this? This is a torque equilibrium problem because we're generating torque from the weight of the kid and the weight of the adult. Those are torques, but we're going to make them equal to each other. Torque equilibrium. So we have balance in the force loop. Okay, Jedi mind powers. So what does that mean? That means that I am going to set up, and we get used to this now, clockwise versus counterclockwise torques. If this is my pivot, the child would generate around that pivot point, what direction is that? Think of a clock. Think of the hands on a clock. That would be counterclockwise. The adult over here is going to cause the seesaw to move in this direction. That is clockwise. The kid is going to get it to move counterclockwise. Now, those two torques are going to be balanced, because that's what we're trying to do. We're trying to get it to be balanced. So they're just kind of sitting there like, oh, look at us, we're balanced. So I'm going to make sure that I set these two equal to each other. They have to be. The counterclockwise and the clockwise torques have to be equal, so I set them equal. Let's put in what torque is equal to. Torque, these are the torques. Torque is equal to force times distance. All right, so force times distance goes on both sides, clockwise and counterclockwise. Let's plug in. Once we've got that idea of what torque equilibrium is, balance between torques, then I set them equal to each other, counterclockwise and clockwise, and then I go ahead and I put FD, because that's what torque is equal to FD, plug it in, solve. Okay. Once I got that set up, it's not that hard, but sometimes if we haven't done this before, that's the hard part, setting it up. So let's put in our stuff. Okay, the kid has a weight of 490, so that's the force. And they are sitting away. Okay, this is a 2-meter board. They are 1 meter away from the fulcrum. We always measure from the pivot point. Distance is always measured from the pivot point. Now, the adult is 120 kilograms. Let's figure out how much force that is. Force is the weight, so 120 times 9.8. So 120 times 9.8 is 1176. 1176 newtons. I forgot my newton over here. I'm going to leave it in. You know, sometimes I do problems without putting the units in. I'll do it this time. I have a newton meter. There's my torque. And here I have a newton. And I'm trying to find the distance that the adult has to be from the pivot point. So I'm calling that x. I'm not sure how far away. Well, actually, what I should do is put that line right here to the pivot. I'm trying to figure out what that is. Not sure. All right, not sure. Okay, so now, what do? Solve the math. I'm going to just multiply 490 times 1, 490, divided by 1176, and I'll have the answer for how far the adult is from the pivot point. So 490 divided by 1176 equals x. And what does that come out to be? 490 divided by 1176 equals 0.4, I'll round it to 2, 0.42 meters. 0.42 meters. In fact, the newtons will cancel, leaving me with meters, and that was what I should get for distance. So 0.42 meters is how far away from the pivot point the adult would have to be. That's 1 meter. That'd be a half a meter. So somewhere in here, the adult would have to sit in order to cause this to be a balanced seesaw. Now, of course, you probably wouldn't. I would be so happy if you would. Next time you go to a playground and you get on a seesaw, calculate and find out and see whether or not it actually works. Do the calculations, sit there, see what happens. Typically, we don't do this, do we? We don't do the calculations. We just get on there and we figure it out. We move until it's balanced. 0.42 meters is the distance from here, and that's the answer for that problem. Okay, so let's do one more problem in this video. I'll break these videos up because these problems get a little more complicated, as you know. That's what happens when you go down in numbers, and so I don't want to make it too long, so we'll do one more problem here. We'll do problem number 8. All right, problem number 8. Here it is. An 8-meter long scaffold. Now, you know what a scaffold is? Like window washers will be on a scaffold, wash your windows on high rises. Painters will use scaffolding. So a scaffold here is being held up by 2 ropes. Right? So there are 2 ropes, or two chains holding up a scaffold. And there's a painter on the scaffold. The scaffold's 8 meters long. Right, it's 8 meters across. Let's see. The scaffold has a weight of 800 newtons. So I'm going to put the weight vector for the scaffold right in the middle, assuming it's a high quality, made in America scaffold. That's 800 newtons. All right. All right, so what else do we have? I'm putting all the weights in. We'll show you why in just a minute. A 1,000 Newton painter stands 1 meter from the left. Here's the left. And if this is 8 meters, that's 4 meters. 2 meters, 1 meter. So this painter is standing about right there. There's our painter. And they have a weight of, I just said it, 1,000 newtons. So 1,000 newtons, a little bit longer arrow than the 800. Try to keep things proportional in my drawing. Okay, 1 meter away. So we know this is 1 meter right here. 1 meter. A 200 Newton toolbox sits 2 meters from the left end. So a 200 meter toolbox, 2 meters from the left end. The left end, so 2 meters right here. Okay, so there's the toolbox. It's 200 newtons, which is, well, that's 800. There's, you know, a little arrow here. Okay, there's the toolbox. All right. A 600 Newton painter is 3 meters from the right side. So let's see, about here from the right side. This is a 600, about that long, Newton painter there. So we have our setup. Lots of stuff going on here. Here's a question. How much weight or force is a weight, weight's a force. How much weight do each one of the ropes hold up? Interesting question. That's kind of weird, right? It's not asking me for torque here. The other problems, we've determined torque and how much torque has to be generated. It didn't say that. This question is asking, how much force do each one of these two ropes hold up? Now your first instinct might be just, well, okay, look at all the force. You have 200 and 800, that's 1,000, 2,600. There's 2,600 newtons of force being held up by the ropes. Divide it in half, call it a problem, move on. Yes, please, please. No, come on, you know it's not going to be that easy, you know that. So no, we don't just divide it in half. You don't get 1,300 and you don't get 1,300 newtons of holding up the weight. You don't split it equal. Well, why not? Because look at this side. A couple of things. You've got more weight on this side, and the heavier painter is closer to that rope. The lighter painter is the only thing on the right side, and that lighter painter is closer to the middle. Which side's holding up most of the weight? You know this. That's holding up most of the weight. Most of the weight is over here. This is going to feel a lot more strain or tension. That's the word we use for ropes and strings when we're talking about forces. We use the word tension. It means force. This is the one that's holding up the most force and has the most tension in it. All right, so how do you solve this problem? Well, here, think of it this way. Let's say that this is my big, huge, it's not a meter stick, it's just this massive thing I taped together. But let's say that this is this. This is in equilibrium. It's not moving, that's what that means. It's not moving, it's not accelerating, it's not going anywhere. It's not accelerating. It's not rotating. It's not moving up, not moving down. If this were to rotate, that'd be a bad day for those painters. Yes, it would. They would not be happy about that, would they? They would fall off and get a boo-boo. So this is in equilibrium. It's not accelerating. It's not going anywhere. Imagine this. Imagine that there's a window here and a person here. Oh, we'll draw the person since, yeah, we'll make the person have an angry face. It's all in the eyebrows. See the eyebrows? Angry face. And this angry, devious person has decided to take a large pair of scissors as they're leaning out this window. Here's my window. Leaning out the window here. And they are going to cut that rope. All right? They're going to cut that rope. Imagine that. Okay? You're not going to be happy painters, are you? No. Because what would happen if this rope breaks or gets cut? What happens? It rotates. It goes around. This would become the pivot point. This rope is attached, so this would rotate and pivot around this point. You see, there are torques involved here. The reason this doesn't rotate is because the torque going up is being balanced by the torque coming down. So we have a counterclockwise, clockwise, like in the last problem, torque equilibrium. If we didn't have a clockwise, counterclockwise torque equilibrium, this thing would tilt to one side or the other. It would rotate. So here's what we're going to do. This is called an equilibrium torque problem. Because if one of these breaks, we're rotating. And since we're not rotating, or an equilibrium. Let's imagine that the rope over here does get cut. What would be my pivot point? This point right here. This would be the PP, the pivot point. Whenever I do a torque equilibrium problem, I always do it from the left side. And the main reason for that is when I'm teaching class, I stay out of the way, otherwise I'm in the way of the problem. This way it keeps me out of the way. You can actually work what's called a torque equilibrium problem from any end. You can work it from this side or you can work it from this side. Now remember the original question. How much force do each one of these ropes hold up? And that's what we're trying to solve for. How would I do that? Well, I know the ropes are holding up all the weight, but not equally. So I know it's not rotating, so therefore it must be in equilibrium. So what I'm going to do is set up clockwise and counterclockwise torques, just like in the last problem. Now I'm going to just shorten those up. I need some room here. So keep those, okay. So what we do is we set up our clockwise and counterclockwise torques. Imagine this on the left side is my pivot. If this is a pivot and we were to cut this rope, which way would this be rotating? What direction is that? Clockwise. That's like a clock. The hands of a clock move this way. That's clockwise. So that would mean, from this point of view, that arrow, that arrow, that arrow, and that arrow, all four arrows generate clockwise torques, causing this to rotate in this direction if we were to cut that rope. Clockwise, 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 shoom, rotation. I have 4 clockwise torques. Now in the last problem, we only had 1 clockwise and 1 counterclockwise. In this problem, we have 1, 2, 3, 4 clockwise torques if we cut that rope around that pivot point. Now, if we imagine that we don't cut the rope, this person's not successful, they try but they can't cut it, and these people are going, no, 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 then this rope holds. This rope isn't going to let that happen. And if this rope doesn't let that happen, doesn't let the clockwise rotation happen, it must be applying counterclockwise torque. Yes, it must be applying counterclockwise torque, bringing these torques into equilibrium, not letting the rotation happen. Okay, so here we go. We have 1, 2, 3, 4 clockwise torques around this pivot point that I chose to work the problem for. This is clockwise, so we're going to set these torques equal to each other. Clockwise. Now, it doesn't. Last problem I put clockwise on the right, counterclockwise on the left, and some of you might want to do that, and that's okay. We'll do that. We'll be consistent. Let's stay consistent. So we'll go counterclockwise, which this must be providing a counterclockwise. That's counterclockwise torque to keep these in check. So these are my clockwise. So here we go. The counterclockwise torque provided by this rope is going to be equal to the force times distance. Okay, force times distance. And over here, I have 1, 2, 3, 4 force times distances. I have 4. I'll do this 4 times. Bear with me. 4 clockwise torques. Fill in what we know. Go ahead and do it. Okay, this is generating the counterclockwise force and therefore the counterclockwise torque. How much force is it generating? I don't know. That's what we're trying to figure out. Remember? We're trying to figure out how much force that rope is holding up. It's a question we originally asked. So I don't know how much force that's holding up. That's what we're trying to solve for. Do I know how far away that force is holding up that scaffold from this pivot point? Yes, that distance of this pull upwards is 8 meters. We're 8 meters from the pivot point. Okay, now I have 1, 2, 3, 4 clockwise torques. Let's do them one at a time. Okay, from this pivot point, everything's measured from the chosen pivot point. It's 1 meter and 1,000. So 1,000 newtons, 1 meter. I'm not going to put the units in this time because it's going to take a lot of room here. Okay, next torque is generated by, so add 200. How far away? That was 2. Remember, it was 2 meters away from that left end, which is my pivot point. Plus, the next arrow I come to is this 800. And it's right in the middle. That's the weight of the scaffold. So it's right in the middle, so that's 4 meters away. It's an 8-meter scaffold, so 4, plus 600 Newton. How far away was that 600 Newton? Well, that was 3 meters from the right, 8 meters total. I have to do everything from the pivot point, so it's 5 meters from that pivot point, okay? 8 minus 3, 5 meters. So 5 meters. Let's do the math. It's a simple algebra problem at this point. We're just solving for how much force that rope is holding up, and that's half the problem will be done. Oh my God, only half the problem? Don't worry, the second part's really easy. Okay, let's solve for x. So let's see. This is 8x equals 1,000 plus 400 plus 3,200 plus 3,000. All right, so that's 3,000, 6,000, 6,200, 6,600, 7,600. 7,600 is equal to 8x. Okay. Divide, get x. X equals, okay, 7,600. Okay, 7,600 divided by 8. 950. 950 newtons. Yay, you're 90% done. But we only have the force being held up by the rope on the right. We have to still do the one on the left and go through this whole thing again. No, you don't. No, no, no. 950 is being held up by that rope. That's the force. 950. Altogether, how much force is there? How much weight is there going down altogether? Remember? 1,000, 2,600. 2,600 the total force being held up by the ropes. So if 2,600 is the total, and we know that this rope is holding up 950, just subtract them. Just do the subtraction. Okay, do the subtraction. We'll do the subtraction, 2,600. I could have done this. I'm just brain dead at this point. I'm tired. So this is my last video for today. Okay, people, I'm tired. Done. That's the answer. Okay, well, 1,650. We started this problem by saying that this rope has to be holding up more than this rope. It makes sense. There's more weight over here. The answer is yes. The math proves it. So this rope is holding up 1,650. This rope is holding up 950 newtons. Add those together, you get the total weight being held up. Now, you could solve for this if you make this a pivot point and go ahead and do the whole thing over again. No, yeah, I don't blame you. I wouldn't do that either. I could have chosen to make this the pivot point. I could have worked the problem from this side of the board. It's more difficult for me to do it. And I could have said, okay, these torques now, those forces would cause 4 counterclockwise torques. And this rope would be countering those in a direction clockwise. But the math would come out to be the same. It would come out to be the same. You don't believe me? I mean, don't believe me. I'm wearing a Hawaiian shirt. Don't believe anybody wears a Hawaiian shirt. Try the math yourself. If you use that your pivot point, and 4 counterclockwise torques here and 1 clockwise torque here, you will get the answer for that, and it'll come out to be 1650. Trust me. There's a long video, people. We got to stop. I'm done for the day. I'll finish the next 2 videos tomorrow. I'm tired. I'm going home eating dinner. Okay? Bye.